Good afternoon, this is Schweitzer. We're looking at a AP Chem review of some top ideas here in AP tests, and that would be the creation of a rate law for kinetics. So, shows up every year on the AP test. All right, so first things first here. All right, so this is reaction mechanisms. All right, so can we create a rate law via the reaction mechanisms? All right, so first things first, let's go ahead and let's write out a overall reaction. All right, so to do that, we want to just, I would encourage you to do all these problems and check your answers. So right from here, some kids always, even though it's still stumble on some of these things. So this Z is produced and consumed. That's an intermediate. Y is brought in and then kicked out the end. That's a catalyst. So it works just like anything else, any other chemical. It's required for X to connect to it. So it's a vital part of the actual reaction. But it is considered a catalyst. So I maybe put it right here. That's where they put it. And then produces W. And both those reactions are exothermic, so I'm going to just put here energy. All right, that's pretty sloppy. That didn't show up very well. Anyway, so the catalyst, that would be Y. All right. Identify the reaction intermediate, that would be Z. On the energy diagram provided, please provide the energy pathway for this reaction. So, all right, pretty important. So we got two steps here. One is going to be, all right, they're both exothermic because they're both giving off energy. This one, however, is going to be the bigger one because it's low. So we start high, we're going to be exothermic and then exothermic like so. Two steps, there we go. On the energy diagram, but maybe we did that already. Move on. All right, can we come up with a rate law for this thing? Determine the rate law for the reaction. Keep in mind, order is the number of collisions in the elementary steps. Okay, that's that order. One would be considered unimolecular, only one item. Two would be two particles colliding together, and three would be tertiary. Three is less common. All right, so and then K is a good way to describe that is the effectiveness of the collisions. Pretend you didn't see that. All right, so all right, so to write this up here, we got slow and fast. So everything in the slow step and feeding the slow step involves the rate law. So anything north of this. So it's going to be rate equals K, and then what's in the slow step connectivity? An X hits a Y. There's one each. So X will be to the first, and Y will be to the first. And it will be second order overall. That's how they describe that. Second order overall. And first order with respect to X, first order with respect to Y. All right, that's that. Next page. All right, look at this guy. Now we got 3 steps. We have a rate determining step here and 3 other steps. All of them happen to be exothermic. So which of the following reaction mechanism could be responsible for this? All right, so 3 steps. This one would be the rate determining step. So this one's out because it's not 3 steps. Exothermic, endothermic. So there might be something here we were looking to adjust here. Exothermic, okay. RP, this one's showing endothermic. I don't know that I agree with that. So in this case, we have exothermic, endothermic, exothermic. So I'm going to go on a limb here and say that none of these really work. And I would want to have this energy on this side. and all of them would be endothermic or exothermic. That's kind of how I see it. All right, move along. All right, so for any reaction mechanism that did not match number 6, create energy diagram for that. All right, well, anyway, let's just do 2 of them here. This guy is exothermic and then endothermic. Okay, so I would say we could do something, and it should say it maybe have a slow step on here. So let's make this one, let's make this one a slow step, and we'll make this one a fast step. So in this point, we go exothermic, so like that. So now top, bottom's lower, that's exothermic. And next one is endothermic, so it's going to end higher, but it's going to have a high peak because it's a slow step. So it's like that. And now it doesn't say if this has to be higher than the start, as if the overall item is endothermic. It doesn't say that. So as long as we're above this peak here, we'd be okay. It's slightly above. Next one, let's do this one. All right, so 3 steps. Exothermic, endothermic, exothermic. Okay, so first one will start here, goes up and comes down. Now let's pick a slow step. Let's do the last one slow. All right, second one is endothermic. So I want to just do this. All right, and the third one is exothermic, but it needs a high peak. Oh, a little higher over that first one. There we go. All right. Ohrs and rate law. Okay, so given the rate law, this would be the rate if the concentration of A is 1.5. All right, well, all we got to do is plug that concentration in there and solve for the rate. 1.5 times 0.05 equals 0.075. All right, so the rate equals 0.075 moles per liter per, doesn't give us time. Okay, so some unit of time, let's say second. Right? We would normally get that time from this guy right there. All right, moving along. What would be the rate if we doubled the concentration of A to 3? All right, well, if we double our concentration, since it's first order, it would just be this guy times 2. All right, and 75 times 2 is what, 150? So we get 0.15, right, equals 0.15 moles per liter per second. Regardless if the concentration is doubled, the rate will what? Okay, regardless if the concentration is doubled, the rate will double. If we triple the concentration, then we expect the rate to triple because it's first order. All right. All right, next one. Now we see a data table here, and there's 2 types of data they can give us. One involves concentrations and initial rate. Keep in mind, this is initial rate. Anytime we have a rate law, rate equals K concentration, this is the initial rate. All right, so this is a guy where we're changing concentrations here, trying to see how it affects the initial rate in order to determine the order and then eventually the K. And all right, so what we do here is a simple little game like this. Okay, it stays. We want actually there's going to be 2 of them here, so let's just write this out here. I'm going to put another guy on here. Right there's good enough. This is going to be A, and this is going to be B. All right, so want to find one where one of them stays the same, the other one double or changes, and see how it affects it. This guy doubles times 2, and this is exactly how I would do it. This guy goes times 2, so this is B is first order. Now here, we want to find one where B stays. So we're not guaranteed to have a nice setup for us, but either way, this one stays the same, this one doubles, and this doesn't change at all. That means the change in A did not, when I doubled this value in this algorithm, it had no effect on this, which means this must be zero order. Okay, and there we go. That's my rate law. This is the answer for number 5. Okay, calculate K, determining including units. All right, you should be able to do this. All right, so the rate, let's just pick a trial number 1. I'm going to go 0.5 equals K times the concentration of A, which is 0.1, 0.1, and it's at zero order. So you could take it out entirely if you'd like. 0.1, and then this guy, now, even though there's a 2 here. Now what this tells me, I'm going to first just finish this problem up here. We'll get back to that. Okay, so 0.1 is 0.01, divide out for the K. So 0.5 divided by 0.01 equals 50. K equals 50. And is meters, moles, okay, well, what are our units in this thing? If this is moles per liter per second, I'm going to divide out a mole per liter. When I divide out a mole per liter, multiply reciprocal, I get 1 over seconds, and that is my units. Okay. Now back to my original thing here. Now this is zero order, okay, and this is first order. It means this is not a one-step reaction. This is likely a multiple-step reaction where in, let's say, step 1, there is a single B involved in this reaction. And this likely produces some intermediate, let's say, I don't know, F. And then F comes in step 2, right, where F might react to, let's say, F plus A to produce C. And this guy is this slow step. So that means I get just one B. That's where that one B shows up. F is intermediate, so it's not going to show up in the overall reaction. And A is beyond the slow step. Actually, we need a second B here because there's two B's there. So likely there's could be another B right here. Either way, B plus A plus F. You could make it a third step and get a B in there if you want. But anyways, it's beyond the slow step. So this B is not counting towards the reaction rate, and neither is the A. All right. Next one. Okay, just got some information here. What is the rate of disappearance of B in trial 4? All right, so this is really the whole point of us making our rate law. That way you can plug in and predict the future. So K is 50 times A, which is 0.3, and B, which is 0.2, and this guy is to the first, this guy is 0. So really the concentration of A doesn't matter. So it's going to be 0.2 times 50 equal and 10. So equals 10 moles per liter per second. Yep, there you go. All right. Again, just note, we have some information here. Integrated rate laws is what we're moving into. These are the 3 integrated rate laws. For whatever reason, they don't have this one on the laminated sheet, which for all the other stuff they put on there, I don't know if they're trying to save space because there's plenty of space, but all you gotta do is take the natural logs off and you have the zero order, so be aware of that. Note the K in these reactions is the same K in the rate law. So in this guy gets put right into here. Okay. Hint, if you need units for K for any reason, I usually use the integrated rate law. I use the rate law, the integrated rate law. So I use this guy to find my units like I just did 2 seconds ago. So and you know, you guys haven't done a ton of it, but eventually you use enough, then the units are just kind of there. You can figure them out or you know them. All right, so for first order reaction starts, we can see the graph. Okay, there we go. For first order reaction, A starts at 0.5 and ends at 0.1 over the course of 50 minutes. What is the rate constant for this reaction? So they just want the rate constant, and we're giving us concentrations over time. So keep in mind, none of these things give a rate. Right? None of these things give a rate, just giving concentrations at certain times. Whenever we're looking at rate, we would be looking at change in concentration over change in time. And unless you're down to an absolutely infinitely small amount of time, it's an average. So if we start with a concentration that's dwindling over time, then what's the average? The average would be from, well, over what area? From start to finish, this line would be the average, right? That would be the average there. If you want from here to here, well, then that would be the straight line right there would be the average. This is not going to give me any of the rates at certain times. It's just going to give me the concentration at certain times, and that's what I'm going to use it for. What's the rate constant? Well, it's first order, so I got to take the first order reaction. This is going to be the natural log of the concentration of now initial time t. This is original. So the time I'm looking for is 50 minutes, and that's the concentration at 50 minutes. That's 0.1 equals negative k. I'm using 50 minutes, and I, of course, want to be aware that I'm using the right time. My k will be have a unit of minutes at that point, plus natural log of concentration of the original times 0, which is 0.5. Pretty straightforward calculation. All right, so I'm going to go, in this case, I'll take the natural log of 0.1 equals minus the natural log of 0.5. So I subtract that natural log off, divide it out by negative 50, and I get 0.0321. So K is equal to 0.0321. It would be 1 over minutes would be my units. That's not asked, but just letting you know. That's a first order reaction, 1 over time. What is the half-life of this reaction? So in this, you can take and use the same thing and go 0.5 to 0.25 and just solve for t. That will tell you the time on half. We do, however, have a shortcut because it's always the same. T1/2 is equal to 0.693 divided by k. This formula is on your laminated sheet, so be aware of that. I'm going to take 0.693 divided by my previous answer, which is the k value, and they're saying it's about 21 minutes, 21 and a half minutes, which seems about right. 21.5 minutes. All right. At what constant? Sorry. All right. It says, next page. Definitely not Grammy Award winning here. All right. So, what would be the concentration of A after 2 half-lives? Okay. Now this one here, you could take and plug in 21, double that time to 43, plug it in there, put the 0.5 in, and solve it out. But we don't want to have to do that. We want to say, okay, well, From 0.5, we have a half-life down to 0.25, another half-life, which is going to be 0.125. Done. What's the concentration after 10 minutes of A at 10 minutes? So you can estimate here because we haven't even gone through half-life, but all you gotta do is take here, go natural log of the concentration equals negative 0.0321 times my time, which is 10 minutes. All right, that's 3, 2, 1, plus natural log of 0.5. And you solve. All right, so we have negative 0.0321 times 10 equals, and then I'll add that to the natural log of 0.5 equals, and I'm getting negative 1.01. Inverse log that, so I'm going to get, in this situation, okay, so make sure you're aware of the math on this. The natural log of the concentration will equal negative 1.01. 1.01. If we inverse log both those sides, second log, natural log, the previous answer, and I get 0.362. All right, the concentration of this thing is equal to 0.362. Of course, that's moles per liter, and makes a heck of a lot of sense. Seeing it started at 0.5, and look at the time that we went through. All right. Student hypothesis. A student proposes this for one-step reaction mechanism for the reaction discussed in this problem. Justify or nullify. All right, so in this case, well, the answer is saying 2A goes to C. All right, so let's just back this up a second, take a look at what we have here. I think they're referring to the previous question. All right, so for this guy, they're saying 2A equals C. All right, so could this work? 2A goes to C as a one-step reaction. I don't, in this answer, I'd say the answer is no. If this is a one-step reaction, then I should have two A's in the determining step, and therefore this A should be second order, not first order. So that answer is absolutely not. Okay. So we're looking at a situation here that if this is it, then this thing should be second order overall. And therefore, we would want probably to have two steps where maybe A goes to B, and then B plus A goes to C. B would cancel. This would be considered the slow step. This would be the fast step, and away we go. Which of the following graphs would legitimately describe the reaction provided? Justify or nullify your each graph. Okay, so it is first order, so we should be aware of all of the charts that describe first order. This is, if you understand this question, this is a legitimate question that I've seen in AP exams. If you know it's natural averages time, that represents a first order reaction, then you're done. Okay. All right, what are the different ways you can calculate K? All right, well, there's three ways. You should know each one. Okay, number one, rate, and that is absolutely the initial rate, equals K times, set the rate law, solve for that guy. Integrated rate law. For this one would be natural log, the concentration equals negative K T plus concentration, natural log of the concentration. And then solve for that guy. If it's a different order, you use a different equation. And finally, this graph, this slope is K. Right? Zero order, if this is zero order, which it wouldn't, zero order had to be straight to actually qualify, but then each of these graphs, the slope represents this. How would I calculate initial rate? There's only one way to calculate initial rate, and it's right here, using the rate law. How do I get the units of K? Well, typically I would use the rate law, right? And I would solve for K. And you should be aware that, goodness, you should be aware that how to solve that units wise. So in this case, well, either way, if you still have a problem with this, just gotta come and see me. We'll sit down and do 2 or 3 of them, and you'll be an expert. Right. Next page. And that's it. Thank you very much.